Swirling clouds of gas and dust stretch light years across the cosmos, stellar nurseries where the universe creates new life. These immense, cold molecular clouds are composed mostly of hydrogen and helium, sprinkled with heavier elements from long-dead stars. Gravity's subtle pull begins the slow collapse of these clouds, sometimes triggered by the shock wave of a nearby supernova. As the cloud contracts, angular momentum flattens it into a spinning disk, the protoplanetary disk, while a dense core forms at the center. At the heart, a protostar emerges, growing hotter as material falls inward, compressing under intense gravity. Eventually, nuclear fusion ignites, and the protostar becomes a new shining star, a beacon in the cosmic darkness. Within the disk, radiation streams outward, balancing the collapse, shaping the environment where planets will take form. The composition of the original stellar nursery dictates the available elements in the disk: light gases for giants, heavy elements for rocky worlds. Metallicity, the abundance of elements heavier than hydrogen and helium, determines planetary diversity across the galaxy. Higher metallicity disks favor the creation of terrestrial planets, rich in rock, metals, and complex chemistry. Lower metallicity regions produce gas giants, massive worlds dominated by hydrogen and helium envelopes. Meanwhile, the turbulent environment of the stellar nursery fosters multiple protostars, each vying for mass and space. Gravitational interactions between stars and disks influence planetary orbits, sometimes ejecting worlds into the void. Nearby massive stars may stir the disk, sculpting eccentric orbits and creating exotic planetary configurations. Collisions between forming planetesimals trigger growth, accretion, and violent reshaping of young planets. Hot Jupiters may migrate inward, their paths shaped by unseen companions or turbulent early environments. Some planets fail to remain bound, becoming rogue worlds wandering the galaxy in eternal darkness. Dust grains coalesce, forming pebbles, rocks, and eventually the building blocks of planets, moons, and asteroids. Ices and volatile compounds accumulate in the outer disk, providing the raw material for gas and ice giants. Rocky planets form closer to the star, where heat drives differentiation and core formation. Early bombardments sculpt surfaces, creating craters, basins, and the chemical layering of nascent worlds. Stellar winds and radiation clear away residual gas, finalizing the architecture of the planetary system. The solar system we inhabit is a product of these cosmic forces, a delicate balance of mass, distance, and gravity. Jupiter and Saturn stabilize orbits, shielding inner planets from catastrophic impacts while shaping asteroid belts. Earth's composition, core formation, and even oceans trace back to the materials delivered from the stellar nursery. Comets and asteroids act as time capsules, preserving the chemical fingerprint of our star-forming region. Variations in other stellar nurseries produce planetary systems radically different from ours, some chaotic, some harmonious. Studying these nurseries allows us to predict where habitable planets might exist beyond our solar system. Every star, every planet, and every comet carries the legacy of its birthplace, a story written in gas and dust. Our cosmic origins reveal that the universe's most colossal structures began in quiet, invisible clouds, shaping the destiny of worlds. Through these birthplaces, we see our connection to the galaxy, understanding how the heavens forge life, matter, and the very fabric of planetary systems.